Imagine trying to sculpt a complex metal part, but you're not melting it down and you're not smashing it with some massive heavy die. Instead, you're pushing it. You're carefully, precisely pushing it into shape one tiny step at a time. Well, this is a real thing. It's called incremental sheet forming, or ISF, and it's a technology that is completely rewriting the rules of manufacturing. So let's dive in and see how it all works. All right, here's our roadmap. We're going to start with why this is such a revolution in the first place. Then, we'll get into the nitty-gritty physics of that push. After that, things get intense. We'll look at what happens when you push metal to its absolute breaking point. But don't worry, we'll cover the brilliant ways engineers are taming the metal, how they master that perfect final finish, and finally, what this incredibly flexible future really looks like. You see, for decades, if you wanted to make a complex shape out of metal, it really meant one thing. You needed these gigantic, incredibly expensive, custom-made dies. And this created a huge barrier, a real roadblock, especially if you were trying to innovate or do any kind of custom work. And this is where you can really see the massive leap forward. Look, traditional forming is a powerhouse for making millions of the same thing, but it's super rigid and costs a fortune to set up. Incremental forming, it's the total opposite. It's a die-less process, which means it's perfect for prototypes, for one-off custom parts, or for small production runs. The flexibility here is, well, it's just staggering. So that brings up a really big question, right? How can one small, simple tool possibly bend and reshape a strong sheet of metal without a mold to press it against? Well, the answer isn't about brute force. It's about localized, progressive force. At its heart, ISF is pretty much what it sounds like. You take a sheet of metal, you clamp it down tight, and then you use a computer-controlled tool to slowly and incrementally push it into a 3D shape. So think of it less like a giant cookie cutter and more like a sculptor's tool, carefully shaping the material. Let's break that down. First, the sheet gets locked into place. It can't move. Second, a CNC machine, which is basically a super precise robot arm, is given a digital map, what we call the toolpath. And finally, that tool follows the map, usually spiraling downwards, pushing the metal just a little bit with each pass, until layer by layer, the final shape emerges. But this is where the real drama begins. Metal is strong. It does not want to change its shape. When you push it, it pushes back. And if you push it just a little too far, it fights you every single step of the way. This is the question that keeps engineers up at night, because the line between a perfectly formed part and a worthless piece of scrap metal is unbelievably thin. So what are the enemies they're actually facing in this process? There are 4 main adversaries here. First, fracture. You push too hard, the metal just gives up and tears. Then there's thinning. You stretch it too much and the walls become dangerously thin and weak. Next up is springback. The moment the tool moves away, the metal, because of its natural elasticity, tries to snap back a little bit, ruining your perfect shape. And finally, all that friction can leave the surface looking rough and scarred. Okay. So with all these massive hurdles, how in the world do you control this chaos? This is where the real genius of modern ISF comes out to play. Engineers have come up with some incredibly clever ways to tame the metal and bend it to their will. The first big idea is actually pretty simple in concept, but totally brilliant in practice. If the metal is being too stubborn, well, you change its properties while you're working on it. You add energy to make it a little more cooperative. And they do this in a few different ways. You can use a laser or an electric current to heat the exact spot that's being formed. A tough material like titanium suddenly becomes much more pliable. Or you can use ultrasonic vibrations. This basically softens the material on a microscopic level, letting it flow more easily around the tool. These aren't just tricks, they're genuine breakthroughs. Now, the second solution tackles that annoying springback problem, and it's really clever. The idea is, okay, if you know the metal is going to bounce back by a certain amount, why not just push it a little bit further to compensate for it? It's a great idea, but to pull it off, you need a system that can think and adapt on the fly. And this is how they do it. As the tool is pushing, sensors are constantly measuring the force. A computer takes that real-world data and compares it to a model of how the metal should be behaving. If it sees a difference, it instantly adjusts the tool's position on the very next pass. It's like this constant, high-speed conversation between the machine and the material, all to achieve perfect accuracy. So, Getting the geometry exactly right is a huge win, but believe it or not, it's only half the battle. For so many applications, we're talking medical implants, aerospace parts, the quality of the surface is just as critical as the shape itself. This quote from the research really nails it. Tribological characteristics is just a fancy way of talking about how surfaces interact when they move against each other, things like friction and wear. A rough surface isn't just a cosmetic flaw, it can seriously degrade the performance and even the lifespan of a part. So getting a smooth finish isn't a nice to have, it's an absolute must. One of the biggest factors here is lubrication, and the right choice makes a huge difference. You can see here a basic paste lubricant. Yeah, the surface ends up pretty rough. Switching to mineral oil is a big step up, but the real game changer is adding nanoparticles to the oil to create what's called a nanofluid. These tiny particles act like microscopic ball bearings, slashing friction and giving you an exceptionally smooth surface. So what happens when you take this level of control, this incredible accuracy, and this amazing flexibility, and you put it all together? Well, you unlock a whole new world of possibilities across a huge range of industries. And the applications are just so exciting. In medicine, this means you can create a cranial plate that perfectly matches the unique shape of a patient's skull after an injury. That was basically unthinkable with old methods. For aerospace and cars, it's all about speed, prototyping and testing new designs in a fraction of the time and cost. And it even opens doors for art and architecture, letting creators make these incredible metal forms that were just physically impossible to build before. And this all brings us to one final big question. We're clearly moving away from the old era of mass production and into a new one of mass customization. In a world that demands solutions tailored specifically to us, from our cars to our bodies, is this die-less, layer-by-layer approach just another option? Or is it the inevitable future of how we make things?